Thank you very much. So thank you guys for being on this call today. As Nicolas said, I'm going to do the first part of the presentation, and then Francois and Pierre actually will do the second part. We are going to focus today on artificial intelligence at the edge. We don't like that terms, I would say, so much artificial intelligence. We prefer to say machine learning, because artificial intelligence is really a buzzword today. So the way we are going to structure the presentation is the following. I'm going to spend roughly 15 minutes. I'm going to talk about Cartesiam and basically the challenges and solution around artificial intelligence in objects. Then I will hand over to Pierre. So I am based in Paris, and Pierre is based in Toulon, in the south of France. And he will do a live creation of a smart vibration sensor. So it's going to do the full presentation from soup to nuts, meaning that starting from the vibrations, creating the machine learning library, embedding that into a microcontroller, and testing live on a bench. So if you stay there in 30 minutes, you will see how to embed libraries, machine learning libraries inside your next IoT without any skills in AI, and then we'll open for Q&A. So a few words about Cartesiam. Cartesiam, we are a software company based in France. We exclusively focus on machine learning at the edge, meaning exactly where a signal turns into a data. And we have offices in the south of France, in Toulon, where the headquarters is located, and then Paris, New York, and Munich, where we have sales and marketing offices. And our mission in life is really to focus on developers, embedded developers. So we talk to the embedded developers, not really to the data scientists. So if you want to talk about linear regression, logistic regression, decision trees, k-mean clusterings, and random forest, that's not really the best place to be today, because what our reason for living at Cartesiam is to make embedded developers happy. Happy because they can create machine learning libraries without any skills in machine learning. That's what we do. So we have a team of PhDs in advanced mathematics, in machine learning, in signal processing, and we spend the few first years of Cartesiam working exactly on this. Oops, my system is not switching. So basically in 2020, we believe that the objects all over the world should be self-aware, meaning that there are 160 billion machines, or sensors, I should say, in the world, and they just don't want to do a better job. Today, we talk about artificial intelligence every day in the press. There is a lot of noise around that. But the reality is really that we just need to make this machine a little bit more smarter than they are today. 15 billion microcontrollers are sold every year. 15 billion Cortex-M microcontrollers are sold every year. And that's really where we focus, because these microcontrollers are into the objects, and by objects could be a plane, could be a car, could be an industrial IoT, could be a dishwasher, could be a vacuum cleaner, could be anything that has got a microcontroller in it. So home maintenance, industrial maintenance, where a pump should anticipate that the bearing is about to break and should alert you through the Sigfox network, anti-fraud detection, security. These are the areas, sorry, where we focus. So maintenance, anti-fraud detection, and security. That's really where we are driving most of the effort for Cartesiam. Today, we believe that the current approach of AI for objects is irrelevant. For the rest, might be true, might be okay, but for objects, it's totally irrelevant. Why? Because first, it's highly depends on the cloud, either for computing power or for sending your data to get a model trained. It relies also on a qualified data set to train your model. So you need to first get the data to train your model, and these data are very difficult to get. Third, you need to have data scientists, and we know that these resources are constrained at the moment. There are 170,000 data scientist jobs open today on LinkedIn just for the US. So most of the company cannot afford a data scientist, and when they have one, this guy is working in the financing department on churns. So very difficult to get a data scientist. And I don't want to comment on computing and energy consumption. So basically what we see in the market in terms of AI is that these projects are expensive, long, very complex, and most of the projects we see today on the market don't go further than a proof of concept. So we worked on that subject since the inception of Cartesiam in 2016, and we spent the first 3 years of the company to work on mathematics and to create our main offering, which is NanoEdge AI Studio. And we believe that with that solution, we have a solution that is first compatible with 100% of the hardware, existing hardware, so the Cartesiam microcontroller. We focus, on embedded developers. So it's really how do we make an embedded developer that is not a data scientist, that is not a mathematics expert, able to embed artificial intelligence inside his solution. We don't need to have any AI skill, no cloud dependency, and no data set. So what we have done is NanoEdge AI Studio, which is working on the PC, and think about this solution like a search engine. We have created 500 million machine learning libraries, and 500 million is basically the combination between the machine learning algorithm, the signal processing algorithm, and the hyperparameters. If you do the combination of these three elements, you end up with 500 million possible combinations. So basically 500 million possible machine learning libraries that will address your problem. So how have we done that? Well, basically we started from scratch. We started from the algebra, from the mathematics, and for 3 years we rewrote from scratch every single machine learning algorithm and signal processing algorithm so they can run inside the microcontroller. Because these algorithms have been in the market for years. Artificial intelligence has been invented in 1954 by John McCarthy, so it's not something new. But these algorithms are geared to server side, so stuff like TensorFlow, Keras, Caffe, and this kind of framework that you see on the right side of the chart. But these frameworks are extremely powerful, but they don't work inside the microcontroller, obviously. So what we have done at Cartesiam is we've created a software for embedded developers that is working autonomously on a PC, and that is able to generate machine learning libraries. And these libraries are ultra optimized, so they are very small. We can go as low as 1.5 kilobytes in size. They are extremely specialized. So you will see in the demonstration that Pierre is going to do in a few minutes how it works. So the way you implement the library is very simple. You create the library on the PC side without any connection to the server. Then you put the library inside the main program of the microcontroller. And then let's say this microcontroller is inside an object that is on machine 1, which is a pump. So during the first minutes or the first days, the microcontroller is going to receive, for example, the vibration data, and it's going to create a model inside the microcontroller that will represent the vibration pattern of this machine. And then it switches automatically to, for example, to inference. And then on the new data, every day, for example, this depends how you decide, you will do the inference based on this model. But if you take this sensor and you put it on a different machine and you start the learning process again, then you are going to create a different model, because this machine, of course, number 2 is different from machine 1. So you will create a machine 2 that is different, model 2 that is different from model 1, and you do the inference based on this dynamically created machine learning model. So this is not just a nice demonstration, it's a real case. It's working today in the real life. So I'm going to talk about a couple of examples. La Croix Électronique, which is a French EMS, is using this technology to anticipate the filter change on the reflow ovens. We have Eolan, which is also a French company that has created a product called Bob Assistant. Bob Assistant is a predictive maintenance solution. So you just put Bob on the machine. During 7 days, Bob is going to learn the pattern of the machine, create the model inside Bob, and then after 7 days, and it's not working 7 days 24/7, it's working every hour, for example, taking a few data to create the model. And then after 7 days, switch to inference, and it will analyze the mathematical distance or the new vibration versus what has been learned inside the microcontroller. And in case of problems, the system will send an information to say, hey, Houston, we have a problem, come and fix the machine. Thousands of Bob have been sold to many companies such as Airbus Industries, to the French railways, to Total, to in Germany, in Veolia, I mean, all over Europe. In Japan, we have a customer who is doing an air conditioning system. They are using here not vibration, but the current pattern to analyze inside the microcontroller the motor control that control the motor that push the air through the filters of the air conditioning system. And just by analyzing the current, the shape of the current, they can anticipate when there is a clogging on the air conditioning system. The beauty here is they did not have to add any additional sensor. It's just a software update. And since we are doing the learning directly on the equipment, whatever the type of filter, a genuine filter or a replacement filter, you start from scratch with a new filter, with a new parameter that becomes the reference, and you do the learning on site. We have also a French Navy that is one of our customers. They are using our solution to create sensors for French submarines. We have no idea what they are doing with it, and that's okay. And trust me, the French Navy doesn't want to share the data. And they like our solution because everything happens on the PC, nothing is connected to the cloud, and therefore the confidentiality is extremely high. In terms of pricing, I don't want to go very deep detail here, but basically we have a design side, which is a PC running on software, and then we have a licensing contract license per object. And you can see the price are extremely slow when compared to having to hire data scientists and so on and so forth. And currently available signals we've been working on are vibration, pressure, VOC, current, magnetic, temperature, ultrasound, and multi-signal sensors. If you have other sensor, call us. It's in French. Sorry, I forgot to translate. We do not work on video and voice, basically because of the limitation of the microcontrollers. And we believe that for industrial equipment, vibrations, current, magnetic, temperature are very, very relevant type of sensors. So this is where we are focusing. We think that, and we trust, and we advise our customers to think like machine, not to think like humans. When you think like humans, you think with the sensor of the humans, which are the video and the voice. When you think like a machine, you think with vibration, pressure, and things like that, which are sensors we are either not good or we don't really have. So today we have partnership with ARM and STMicroelectronics, and these two companies, we are AI partners. For analog device and Silicon Labs, others are in the pipe. STMicroelectronics tested our technology, and they said that we blew their minds, and you can see that on their website. We announced basically last week a new version of the software that is 100% compatible with the new development card of STMicroelectronics. And from Gartner, from the analyst, Gartner last year in 2019 said that there are 3 vendors in the world that are relevant on the Edge AI. 2 are STMicroelectronics and Renesas, and the third one is Cartesiam. And last week they just announced the new edition of the Cool Vendor in 2020 IoT, and out of the 4 companies, Cartesiam is one of them. And in terms of industry, we won a couple of prizes. I just want to mention, for example, the MEMS and Sensor Congress in San Diego last year, and the IoT World Congress in Barcelona also end of last year. So in summary, and I just want to leave most of the time for the presentation of the live presentation. If you want to integrate anomaly detection in your products and you want to do it fast without investing heavily in data science, data set, etc., and whatever the industry you want to do, either predictive maintenance inside your product, fraud detection or security, NanoEdge AI Studio is a good way to go because it's, of course, easy, fast, and affordable. And I strongly encourage you to go on our website and to download the studio. You go on Cartesiam.ai. You can download the studio. You have a free version that's going to work for 2 months for you, so you have plenty of time to test it. And if you want to have a personalized demonstration or any question, feel free to ask contact at Cartesiam. I will receive the email myself directly, and I will help you in your request. Now, I'm done with this first part. So Nicolas, maybe if you can hand over to Pierre, who is going to take the lead now and do the live presentation on the creation of a smart sensor.
Thanks a lot, Joel. Pierre, you have now the presenting rights, and here we can see your desktop, so everything is fine. A reminder to participants, please use the questions feature to ask any question you have, and we will go over them at the end of Pierre's presentation to address them and make sure you get everything you need to know about AI on the edge and the Cartesiam SDK for embedded developers.
All right.
Here we go. The floor is yours, Pierre.
Yes. So hello, everyone. Can you see my screen? Can you hear me well?
We see your logo at the moment. Perfect.
Yes. Perfect. Perfect. Okay. So here I am. Hello, everyone. You can see all of that. Is the font okay? It's not too small to read?
Yeah, Pierre, perfect. Sound is perfect, and split screen is fine as well.
All right, fair enough. So I'm Pierre Guiglion. I'm a support engineer at Cartesiam, based off Toulon in the south of France. I joined about 6 months ago, and at this time I knew very little about machine learning and even less about embedded development. So as Joel said, machine learning and AI these days, they've become very big words. So I was excited, but at the same time, I was a bit anxious that not sure I could wrap my head around all of that. So what I see is that today I can just use NanoEdge AI Studio and start a project from scratch, even without knowing anything about data science. I can take a data logger. I can here simulate a use case, as I will show you in a moment. I can log some data live on my computer and then use this data to give examples of what a good signal or a bad signal means, then find a library that is most suitable given my use case, and even test this library before I embed it. And finally, using any third-party IDE, like I'll show you today, or even embed, you can start very easily. So that's what I'm going to show you. So yeah, that's the real strength of the studio, is that you can basically do everything quite easily. It's a free software. So I'll show you here the Cartesiam website, Cartesiam.ai. Go there /download to download a free version of the studio. You can basically do everything for free, and even go to the library deployment if you're using one of the authorized boards, as the one I'm using here. So it's a ST microelectronic board, as you will see in a moment in the studio. Okay. So here we also have a few tutorials that take you step by step through from A to Z to create a smart device on your own. Here it's pretty similar to what I'm going to show you. It's a vibration sensor, but you also have a current sensor to detect if, for example, the bag of your vacuum cleaner is clogged or not. And we also have a bunch of other tutorials, for example, to detect when your coffee is ready, or if you're playing the right chords on the ukulele or an acoustic guitar. So we're basically compatible with all ARM Cortex-M architectures. So it covers almost every case you can find. And what's really great about the studio, its real strength is that it gives you a new way to design algorithms, a new way to create code. It gives you, the purpose is to find the AI library that is most relevant to your use case. As Joël mentioned just before, you have about 500 million different combinations of what we call a AI library, which is a machine learning algorithms coupled with a way to treat the signal and also some hyperparameters. And you have lots of them. So the purpose of the studio is to find the best one, the most relevant one for the use case, and start testing it right away. And then using this library in your existing hardware, you can use the functions that we provide, the smart functions that are mainly initialize, learn and detect, and start coding fun features. So here I'll turn on my demo. So sometimes using a bit of machine learning can go a long way, and it's very useful to solve some problems. In our case here, I have two rotating fans that simulate vibrating patterns on a machine. So here you can see that they both work at the same time, then one of them stops, and so on and so forth, to create some kind of interesting pattern, not something that is too straightforward. And also on that machine, well, it makes the whole box vibrate, right? So with my SD card here with the accelerometer, I can just sense the vibration patterns on this box. And then I have a few ways to introduce anomalies. So what I can do, for example, is just cover some of the fans like that. I can tap the fans gently, or I can put it in overdrive and, to increase the speed of the fans. So without the studio, if you're very lucky, what you would need to do is use the threshold if you can get away with it. But here, it's not a simple use case. Our vibration patterns are almost the same intensity. So what you would need to do is carefully extract the features from the signal, the vibration patterns, and then set thresholds on each of those features, for example, using FFT or something. So you can imagine that it can be a very time-consuming process and require lots of signal expertise and at least some knowledge about the use case. So using the studio is much more straightforward. So here with the studio, we just start from the embedded world and from the sensors, and we really teach the library using examples what a good signal is. So for example, all of this happens inside the microcontroller, and this is very, very important. For example, for Sigfox users, it makes very little sense to stream all this accelerometer data over the network to use it on the cloud later for processing. Instead, here what we will do is treat it where it is produced on the sensor itself. So everything happens locally in situ. So let's go ahead and see how it works. So here I'll just go from the very beginning, from scratch. I'll just go ahead and create a new project. So I'll just call it demo. I can choose a target. We support any ARM Cortex-M. And also we have two authorized boards. The one that I'm using today is L432KC. That enables you to go all the way to library creation. And here you put the maximum amount of RAM in kilobytes that you wish to dedicate to the machine learning on the microcontroller. Then you select your type of sensor. here I have a 3-axis accelerometer, so I'll select that. But you can also use magnetometer or current sensor, and so on and so forth. So I'll create the project, and now I am at step 2. So you can see here the progress bar, very straightforward. I can directly select what I call regular signals. So this is where I will give the studio some examples of what a good signal is. And to do that, you can use a file that you have created before. For example, here I have a bunch, nominal, anomaly, and so on. But what is more interesting is to use live data. So here I happen to have an accelerometer that is connected to my serial port through USB. And I'll just use that port. I can quickly also show you what kind of data I get from this accelerometer. So here I just open the terminal, and you can see what goes out of the electronic board. Just XYZ accelerations, one after the other, 256 times. So here I'll select a maximum number of lines, let's say 50 lines, 50 examples, and click record. So here I'm now recording examples of what the vibration patterns that are happening live on this box. And it will basically help for the library selection process to pick the right algorithm for this particular use case. So here, I don't know if the refresh rate is fast enough. I'm about 34 lines. I hope everything's smooth on your end.
Yeah,
here
it's fine.
Okay, okay. Great. So here the delimiter that I'm using is a space. So you will see later after it's finished logging, yes, now that everything looks correct. But if you're using a comma, for example, you can select it here. Here you see that I have 768 columns because I have 3 axes on my accelerometer and 256 of buffer size for each axis. So now I'll validate this import. And here I see a preview of my data on the 3 axes. Again, I have imported 50 lines and 768 values per line. Here you have a bunch of checks to make sure that everything is fine, that you only have numerical data on your lines, and to check for other errors. Some of them are blocking, meaning that you have to go back to your file and check that everything is fine and fix the issues. And others are just warnings. So here we have now the regular examples when everything is working as intended. So I'll go to next step, step 3, and this is where I need to give some kind of examples of what it means to have an anomaly on my system. So it can be anything, and you don't have to be exhaustive at all. Anyway, it would be impossible to be exhaustive. You can never predict all the different kinds of anomalies that you will get. So here, what I will do is just cover the fans with a post-it. It's very premium anomaly, very high quality, as you can see. And same as before, I log about 50 lines, 50 examples of this kind of anomaly, and click record. So now, hopefully, the vibration patterns on this box have been changed enough so that later in the next step in benchmark, the algorithms can find a library that is good enough so that it separates those two things. What is important to understand is that these examples of bad signals, they are not used to do any learning, because the learning happens in situ, right? And here I'm in the studio, so I'm not in situ yet. This is because, as we said, we have lots and lots of possible combinations, possible libraries, and we just need to give some context for the research. But at the end, when we export the library and when we embed it into our microcontroller, it will be completely blank. It will know how to learn because of its parameters and so on, but it will have no knowledge at all. So we'll need to do another learning phase from scratch. So now the anomalies have been recorded. I can validate the import. And again, you will see that all the checks look good. My data looks funny, a bit wavy. So I'm happy with that, and I can go on and proceed to the next phase, which is benchmark. So this is where the studio will do basically all the heavy lifting for you. You've given 2 examples. Here you see that they look somewhat different, but we'll see what happens. And validate. So here, all the millions of libraries are tested. They're not all tested by brute force. We have a smart way of doing it, but each of them is tested, and we do a learning phase and a detection phase, and we compare the performances. And the way that we gauge those performances are with 3 markers, 3 indicators. The first one being the balanced accuracy. So this is the one that is optimized first in first priority. And you can see here in this graph, it's a summary of the performance of the library that is being analyzed at this moment. The red and blue dots show the performance when running a detection step on each signal examples provided in the steps before. So the balanced accuracy is how well the library can correctly attribute the good signals, to correctly classify the good signals as good, right? Put them at 100% similarity, and correctly classify the bad signals as bad. So here, by the way, this percentage similarity just measures the mathematical difference that there is between the knowledge learned and the signal that we see at instant t. Now, the next thing that we optimize after that is confidence. And confidence is the ability of the library to put as much distance as possible between the good data and the bad data. So here, for 100% confidence, what we would need is all the blue points, all the nominal signals at 100, and all the abnormal signals at 0%. Finally, when all that is good, we try to minimize the RAM used. So you saw just before in the project creation, I just put 32 kilobytes. That can sound a bit too much, maybe, depending on the use case. But in practice, it's much less than that. So here we have 4 kilobytes. It can go as small as 2 kilobytes. And maybe it oscillates between 2 and, I don't know, 10, 15 kilobytes at most. But it heavily depends on the use case, of course. Okay, so the performances so far, they look decent. It looks like there's some kind of separation already, even though the benchmark has been running for only 2 minutes and 45 seconds. And we've only tested 879 libraries out of 500 million. And you can see that just now the performance have improved just slightly. So what I will do is just stop the benchmark as it is to show you the later steps. But if we wanted, we could go ahead and go to the testing phases even without stopping the benchmark. So for quick testing, it's useful to do. And you can even deploy a library without ending the benchmark, but I'll just end it here. So here you will have a summary screen that gives you a very important indication, which is the minimum number of learning iterations to learn in the next phase when we embed the library. So here you see 20 iterations. So remember that I learned 50 examples for each, and now it tells me that actually it looks like 20 should be enough. If you give 20 examples of good signals, it should be enough. So I'll go ahead and test my library performances using the emulator very quickly. So by the way, all that happens on your computer. Nothing leaves your computer at all, which means that there will be no problem of confidentiality, that your data is secure. So I'll click initialize my emulator, and I learn again from the serial, from my serial port. I'll just do 20 iteration as it was recommended by the studio. So now it does the learning. Well, I don't know if you can see what I'm doing now is actually learning with the post-it because I forgot to remove them. So I'm learning a slightly different case to the data that I used for benchmark. So that will be interesting. So now using this slightly weird setup, I can go to detection and see if my percentages similarity are good. So here I haven't changed anything from the learning step, so everything stays at 100%. So now if I remove the post-it, you see that the similarity drops because there's an anomaly. And we really did the learning in situ because you see I didn't learn exactly the same thing. I can put the fans in overdrive. The similarity drops again. I can go back to normal. And hopefully goes back to 100%. So now we're happy with our performances. We've tested everything, looks good. We can go to the final step where we deploy the library. So here you have a code example, you have a few parameters to check. Can go ahead and have a look, but I'll just compile the library in development version. The production version is a slightly different version that there's little cost associated per device if you start mass producing your device. But for the moment, I'll just use prototype. Okay, so what you get is a zip file, and in that zip file, there is the static library, the best one that was selected by the studio, lib-neai.a. And you don't see that, so here you should see it now. The static library. So now that we have the library, we will use a third-party software, which is, in my case, because I'm using a ST board, it's STM32Cube IDE. So you can see here the lib-neai.a that I just imported. Here's the code. It's my main code that I can design the way that I want. I'm completely free to design any feature here. It was previously in data logging mode, so I'm going to remove this data logging mode by commenting out this line. Here I have one of the three most important functions, NanoEdge AI initialize. The second one is NanoEdge AI learn to start the learning process. And of course, I pass an accelerometer buffer to that function. And finally, where is it? Here, you have the NanoEdge AI detect function, where again, I pass an accelerometer buffer, and I get as a result a percentage of similarity. So I can, craft any feature. I can use this similarity percentage to trigger any kind of function, any kind of alert, to ring a bell, or, you can be creative. So I'll go ahead and save that and compile. Okay, looks good. So now here, everything should happen. Okay, I'll just reset that. Okay, so now I'm doing the learning directly on the board in situ, and you can see the progress here on the terminal. So now it's not the emulator anymore. Everything's happening on the board with the library. So it's about 50%. I'm doing maybe 75 iterations of learning just to be safe. And here I'm learning the nominal patterns as I showed you before. So here it's set up so that right after learning, it starts detecting. So here nothing has changed. If I tap the fans gently, you see that the similarity drops back to 100%. If I put a post-it to block one of the fans, it drops. And if I put the fans in overdrive, then it drops as well. And of course, I can just start now learning something else. So if I reset here, I'll learn from the beginning. So I just run NanoEdge AI initialize to wipe all the knowledge. And now I'm learning what was previously the anomaly, but now it's considered to be normal behavior. And you will see, just as before, that, well, we're able to choose what we want to learn. And also, you don't have to reset the knowledge before you do a learning phase. You can, if something has changed in your setup and you want to take into account those modifications, you can just run a new learning phase to complement the knowledge, to enrich it. So here, again, I'm 100%, even in overdrive mode. So if I block the fans, again, I see a similarity drop. Okay, so hopefully this demo will be helpful to understand what's really in play here and how easy it is to use this tool. I did everything with you from beginning to the end. I could have let the benchmark run for a bit longer. It would have created even better results, but basically you see how easy it is. So now if you have any questions, I'll be happy to answer them. And thank you for your attention.
Thanks a lot, Pierre. Very interesting. Even if you let the post-it on place at the beginning. Thanks a lot for that. We already have
them, but it proved my points. Kind of, it helped me a bit.
Yeah. Trust me, I've done and seen much more biggest mistake on live demos. So this one was a good one. And for everyone, it's important to understand how brave it is to go into a live demonstration like that, because usually it does not go as expected. So thanks again, Pierre. We already have several questions, but feel free to ask if you have anything else you want to learn. So I'll go over what we have. Yes, we've got Jose saying outstanding demo. So
thank you, Jose.
You've got a fan already?
Thank you very much. Here you have all the documentation, by the way. All the links that I showed you before that point to the tutorials.
First, great. Okay, so there if you want to get into the full documentation. So first question is from Sarah. Sarah was asking if there were any plans to get your software in a Sigfox solution like the Bob sensor Joel mentioned, which I should say it was not a Sigfox device, but a LoRaWAN device. So either any plans to do the similar stuff in Sigfox, or do you offer your toolkit for other companies to do it?
Okay, so this is Joel. The point is the following. The Bob has been done by a company called Eolan, and they have decided to go with LoRa. Shame on them. But we know that there are currently other companies that are thinking about doing the similar type of sensor solution for predictive maintenance with different type of MEMS and capacities. And we don't know yet at the moment what they are going to use in terms of, let's say, network. But I should say that as far as Cartesiam is concerned, I would say that this is not on our plate. We offer the solution to do the learning in the object and do the analysis or the inference inside the object. Now, after the anomaly detection has been done, whether you want just to blink a LED or you want to send through a Sigfox or you want to send it through another type of network, I would say this is the responsibility of the person who is designing the object based on considerations such as coverage and other things like that. This is not on the Cartesian side.
Okay, so Asala, this means that Cartesian is an enabler, and as you were saying that this solution sounds like a game changer for predictive maintenance. It means that you are free to build it yourself and to grab the opportunity. So that's even more good news.
Yeah.
So another question, this one from Alexander. Ouch, I missed that one during the live session. So I don't know, it was close to the beginning of your presentation, Pierre. It was asking during the data recording, the numbers we were seeing, there are non-scaled values from the accelerometer and not physical acceleration values, right? Don't know if that makes sense, and maybe I'm not understanding the question right.
So the numbers are accelerations along X, Y, Z axes in milli-G, and
okay.
all separated by spaces. So basically you have acceleration along X, along Y, along Z, which represents one sample, and then you do another sample, and then another, and then another, 256 times. So you end up with 768 values, and this is a snapshot or a signal example, and then you repeat that. So here in my case I did 50 times that.
Okay.
So, from the accelerometer in milli-G.
Okay, so Alexander, I hope it's answered your question and that I did not butcher the question. Another question, again by Alexander, he was asking if the duration of the model training itself was depending on the nature of data. And does it depend also on the variety of the source signal patterns that you are using?
Of course, the way that you learn patterns heavily depends on the use case. So when you start using the studio, you don't really know how much examples you will need to give. So you give as many as you can and then proceed to the next step. Again, give as many anomaly examples as you can, and then proceed to the benchmark. And there you will see very quickly if it looks promising or not. You saw that in my case, in a couple of minutes, I saw some kind of separation between the good data and the bad data, kind of. But sometimes you will see that after 1 hour, 2 hours, a few hours, everything looks very random. So maybe it's a sign that you need to go back to your data logging methodology, change a few parameters like maybe sampling frequency or the size of the buffer or something else, or maybe the sensitivity of your sensor.
Okay.
Yeah, so this is something that you can see also on the graphs as I'm showing you here.
Yeah.
You can have good visual feedback, but sometimes it will take a long time. You need lots of examples, and sometimes, as in today's case, you don't need much. 50 is enough.
Yeah.
One point.
So, yeah, go ahead, Joel.
Sorry, Nicolas. Just one point to add to what Pierre just said. We are also doing recurrent learning, meaning that incremental learning, meaning that you can, for example, be on a machine and do a learning pattern during summer, for example. And if in the winter the conditions are different and therefore the vibrations are different, you can just, through Sigfox, just launch a ping and say, learn again. And then the system internally will complement the learning inside the object. So you don't have to go and flash again with a new code. Locally, you can create a new learning and increment the learning and do the winter, the summer, etc. So you have the full pattern. This is a very
okay. Okay, thank you. Because we have a related question from Hugo, who was asking especially about long time data acquisition. So let's say, for example, you have very long operating cycles, and so you need to keep your device for maybe up to 1 year in operations to get the normal baseline. Is that something which is possible to have such a long learning cycle?
Yes, of course. The way it works is that you have those functions. You have the learn function, the detect function, and you can call them at the frequency that you want, depending on the use case. So, if, for example, if your use case has several regimes, several modes of nominal behavior over a few months, then you can run a few iterations, maybe a few each day, for a month, to acquire this baseline knowledge, this reference knowledge. And even if you forgot some regime, you can still log it later. So after you start detecting, it's not over. You can always go back, run a few more learning iterations, and all the regimes, all the modes of functioning, but they have to be nominal, right? They have to be normal. They have to be learned, all of them.
Well, what we have done, Nicolas, just in the light of this example, is we have learned the pattern of consumption of gas, electricity, and water for a full house for 3 months in a row, which was enough. Huh? So signal is really whatever they want. It could be, like, for example, we've been working on circuit breaker just to learn the click and clack when you turn on and off a circuit breaker. So it's extremely short signal. And we've been learning, as I said, a signal over a period of 3 months for water, gas, and electricity consumption for a house. So it could be absolutely anything. And as I said earlier on, you can still complement your learning later on by doing incremental learning. So you do not erase your learning, you just add additional pattern in a learning that has already been done.
Okay. We have a lot of questions. Get ready, Pierre.
Shoot.
A lot. So you got people all excited. So that's good. Good sign. I've got Lionel asking if the system is able to distinguish more than 2 classes.
So as of now, the system learns a normal mode of behavior, and then everything that does not correspond to the patterns that were learned is considered as an anomaly. So you have the good and the bad classes, so just only 2 classes. We're working on implementing some kind of classification feature, but it's still in development, and we don't know yet when it will be in production. But this is something that can't be done at the moment. What you can do, however, is because you can craft the code in any way you want, you can keep the buffers that you pass to the learn and to the detect functions, and you can do whatever you want with those. So you can save them. For example, if you have a bad return value from the detection step, you can just put that aside and constitute some knowledge, some internal knowledge that you can use yourself, that you can analyze yourself, and maybe you can compare the other buffers, possibly corresponding to other anomalies detected later on, to these previous cases. So this is something that you can do already, but we don't have yet a way to distinguish between more than two cases.
Short answer, Nicolas, the system has been designed to do anomaly detection at the moment. And for anomaly detection, it's working perfectly. If you want to do classification, let's say, come back in September.
Okay. You were mentioning the learning function, Pierre. Question from Hugo again. If you have several sensors, do you need to call the learning function for each of them that you want to use to feed your models?
So it's a good thing you mentioned that. We're developing this feature to have multi-sensor. It's almost in production. We're testing it these days. If you go ahead and download the version today, you won't have the possibility to do that. You can only have one sensor at a time. For example, a 3-axis accelerometer or a 1-axis temperature sensor or something like that. But if you want to have, again, for example, 3-axis accelerometer with a 3-axis gyro with a 3-axis magnetometer plus a temperature, so that's 10 axes, right? This is something that you will be able to do very soon, and you will be able to select like an axis in this screen here in the project creation. So actually, because I'm using a development version, you can see it here already, but it's not out yet. And by selecting that, you will be able to do it. So it will change the formatting of the data that you import, but now you will be able to get some more results during benchmark that can work well with multi-sensor.
Okay.
Short answer
Thanks.
is come back in 2 weeks.
Yes.
Okay, so a lot of new features coming up.
Oh yeah.
Good. I have a question from Alessandro. And Joel, you mentioned initially how critical in IoT are component cost and energy consumption. So related to that, Alessandro asked, what's the recommended hardware, especially regarding a RAM memory and so on? What the minimum or recommended hardware setup to be able to properly run your toolkit?
Well, actually, it works the other way around. You tell us how much RAM you allocate to the library, and we will create the best library in that environment. Usually, the library, the minimum, the smallest one we've seen is 1.5 kilobytes, and usually it range in size of, let's say, 10, 12 kilobytes of RAM and 100 in flash.
Yeah, if the flash size, I checked very recently actually, and it ranges between 3 kilobytes and 20 kilobytes of RAM, all the libraries that we've compiled so far.
Oh, okay, so it's even better.
Yeah.
Okay.
Okay, thank you. I'm sorry, I'm trying when I can to put questions together when they're around the same topic, but sometimes it's going to be left and right. And so another topic, Andre is telling us that from his point of view, this is supervised learning, your demo, supervised learning as patterns of normal data and anomalies that you fed into the algorithm. And he was asking, where is the unsupervised part?
Well, the unsupervised part comes from the fact that when you have your library, it's just some piece of code, right? You put it in your microcontroller and you don't have to give anything else than raw data logged on a machine that's working properly. So you just put it in your machine, for example, just after a maintenance cycle, and then you start logging data. After a few iterations, you start detecting. So there's no indication whatsoever given to the software about what an anomaly looks like. And you saw that, that's what I showed. Even if I selected a library that was designed to detect something without a post-it on it, actually, because it's unsupervised in situ, when I embedded the library, I could learn even with the post-it. So it really adapts to each machine, right?
Yeah, there is a trick here. We just put the system in a condition where we have only one pattern to learn, which is unsupervised. Of course, the machine is working well because it's just out of maintenance, or the machine is brand new, or the filter has been changed, or whatever. We know the machine is doing good. And we say, learn that. Learn by yourself. So then it gets the data, create the learning inside the microcontroller. And then after a couple of minutes, seconds, days, whatever, we'll turn to, now I'm listening to the new patterns, and I will tell you if there is an anomaly. So that's why we call it unsupervised learning. You don't teach anything.
Okay. What did I have? Alexander was asking if you could please describe, basically was looking for more details about the difference between the learning you've done on the PC and the learning at the edge itself.
So on the PC, I did 2 data logs. The first one here to give regular signal examples. The second one here to give abnormal signal examples. And this is just to select out of 500 million, one library that is best fit to our use case, to our vibrating box. Then I did another learning, this time using the best library that was found. Well, not exactly the library because it was not embedded yet. I used the emulator associated to that library, which is just a clone of the library that here I'm using within the interface of the studio, but you can download it for Linux, for Windows, and so on. So here I'm using this emulator to learn only the regular signals that I captured from the serial port. So I didn't give any example of anomalies here. So in this case, it was unsupervised learning. And later on, I run another learning phase, this time completely outside of the studio. When I went back to my code and unchecked my here data logging flag, I turned it into a self-reliant smart device, right? So I did another learning phase on this device, not on the emulator anymore, but locally using the library itself this time. And again, I just learned some data and told nothing about potential anomalies. So hopefully the difference between all these different cases, especially between the data that you give for library selection and the unsupervised learning when you use the library itself or the emulator. I hope it's clear enough. If it's not, don't hesitate to ask more questions.
Yeah, don't hesitate to use the question box if you need even more clarification. What was the sampling rate again that you used during the demo?
So for this, we had 256 of buffer 256. Size, 256 per axis. So it was, so you can see it here, right? Samples, 256 samples per axis.
Okay, so that's very easy to adjust your sampling rate to whatever is useful or needed for your own use case.
With the sampling frequency and this buffer length, then you can determine the length of the signal that you want to capture. So make sure that this is coherent with the use case, and then you're good to go.
Okay, we are almost there in regard to questions.
Great.
Jose was asking if you could have 2 different libraries running, allowing you to create more than one good case.
So this is a smart question. Indeed, if you have more than one libraries, you can, detect, like, for example, 3 classes or more. That's not something that is possible to do as is today, because of the way the libraries are designed and the way the functions are designed. It would be possible, but it would require some more work on our end. It's not something that is designed to be possible to do, right? For the moment, it's only designed for one sensor, and in a couple of weeks for multi-sensor. So then using multi-sensor, you will be able to to use several sensors, and even later on, not sure when, you'll be able to distinguish between several classes. But not yet.
Great. And we have one. So far, that's the last question. If you have a last question, you can still add it. So right now, the last question is from. Oh, you melted into your background, Pierre.
Yes.
So the question from Vincent was asking, maybe is that in your roadmap, basically to have any regressions use cases?
Any
regression use case?
Not sure I understand. Sorry.
So I'm not sure, Vincent, if you're asking about the regression on the behavior of the system or regression at the model used behind.
Oh yeah. Okay.
Vincent, if you can elaborate, maybe.
So you mean maybe to predict some kind of failure in the future, given the similarity scores that were returned with the detect function, for example? There's something that we initially implemented in the past, in previous versions, that was called forecasting, to be able to predict when a critical failure was bound to happen. And we decided finally to take it out of the library, but instead release it later as an open source tool, because the way it worked was take into account the similarity scores, and based on these similarity scores, which is just one way of looking at the distance between the model and the signals, then gauge the distance from nominal behavior. So we use that to predict some time to failure. But again, it's just one way of doing it. So we'll release that in the future as an open source tool. But there's plenty of other ways, like regression, any kind of regression, and you have tools for that anywhere online. You can find them. There's many ways to do it. So I'm not sure if the question was about that or something else. Sorry.
Yeah, spot on. Vincent confirmed that he was speaking about prediction model,
right.
regression model to be able to do forecasting. So cool. You were spot on. So thanks a lot. I think we're done with all of the questions. Congratulations. Thank you and congratulations, Pierre. We have a lot, alongside the numerous questions, we had a lot of messages thanking you for the quality of the demo and the quality of the setup, which basically ashamed me when I remember some of the bad live demonstration that I did online. So thank you for that.
If only I could dissolve into my background again, it would be great. Yeah, but if you have any other questions, in case we didn't have enough time to answer all the questions, you can just send an email to either myself or support@cartesiam.com, and we'll be happy to answer all of them.
Okay, thank you. And we will send you an email to all participants with the right contact information and so on. So thanks a lot. And just for your information, we had questions from all over the place. From the name, I know at least we had people from France, Russia, Brazil, UAE, asking questions, and even more countries in the participant list. So pretty impressive. So thanks a lot again, Joel and Pierre, for that presentation. I hope it was useful to all participants. Welcome.
Thank you very much, Nicolas. Thank you very much, Nicolas, on your side. It was very well organized, and it's a pleasure to be with you. And to all the participants, yeah, you can go on the website, download the software, Cartesiam.ai, and play with it. It's free, and would love to hear from you. Just drop us a mail on contact@cartesiam.com, and we'll be happy to engage with you wherever you are on the planet.
Thanks a lot. And I'm very happy that we managed to organize that session, because basically for the people that are used to join our webinars, this one was less directly Sigfox related than some of the other presentations we did in the past. But I truly believe this kind of solution has a high potential for IoT in general, hopefully for Sigfox-based solutions in particular, but all in all, I think it could be a very useful tool for the solutions that you or your teams will build in the future. So I'm very happy that we managed to get this great informative session today, and highly technical, which also was a bit new, but I'm very happy to see that the audience was very responsive to that. So thanks to all. So we will send a follow-up with all the information, everything you need to have following that presentation. And this recording will be made available on YouTube, as I said. Sorry, I'm losing my voice. So recording will be available on YouTube by Monday latest. And basically, so thanks all for joining us today. Enjoy your day, or the rest of your day, depending on your time zone, and stay safe, and hopefully see you soon in other online sessions. Bye-bye.
Thank you. Bye.